everybody for the introduction and for the invitation, and thank you to all of you for coming. So let me first see if I can successfully share my screen. Great, yeah, so hopefully everyone can see that now. Let me know if the dark mode is unreadable or
The green on black is a little difficult to read for me.
Okay, I'll try and avoid using the green. Maybe I'll just keep it to white. Okay, so perhaps the starting point for this work is this theorem due to Fomin and Zelevinsky, which says that there is a bijection between, on the one hand, clusters in the AN cluster algebra, and on the other hand, triangulations of a convex n+3 gone. So yeah, no need to worry for the purpose of this talk what a cluster algebra is, but yeah, some commutative ring with distinguished generators called cluster variables, which come in sets called clusters. Okay, so yeah, the triangulated categories is in the title of the seminar. So there are some triangulated categories lurking around. So in particular, Buan, Marsh, Reineke, Reiten, and Todorov define these so-called cluster categories, which somehow categorify cluster algebras. So in particular, given a cyclic quiver, so directed graph Q, Buan, Marsh, Reineke, Reiten, and Todorov defined the cluster category as follows. So we'll see an example of this a bit later in the talk, so it's maybe a bit abstract if you haven't seen it before, but yeah, I'm denoting the cluster category CQ. We start by taking just the derived category of the path algebra of Q over some field K, and then we take the category of orbits of the functor nu shift by -2, where nu is the Serre functor on the derived category. And yeah, -2 is just the usual shift by -2. By work of Keller, this is in fact a triangulated category. And in this triangulated category, they live certain objects called cluster tilting objects. And yeah, if we look at the cluster category of an AN quiver, and we take the basic cluster tilting objects, so which don't contain any repeated direct summands, then yeah, we also get these objects in the bijection as well. So okay, so we have this bijection involving two-dimensional triangulations, but yeah, I guess way back in my PhD thesis, I found that there's also a bijection you can get with certain three-dimensional triangulations. So yeah, there's a bijection. So our three-dimensional triangulations are triangulations of a three-dimensional cyclic polytope. So yeah, some three-dimensional polytope, which I won't define, which has n+3 vertices. And now the algebraic objects which are in bijection with these are now not cluster tilting objects, but these certain sequences of cluster tilting objects, which are called maximal green sequences. And yeah, now we need to actually pick an orientation of our AN quiver. So yeah, a linearly oriented AN. So yeah, that quiver. Modulo some equivalence relation, which I studied in joint work with Michal Gorski. So yeah, this theorem is already out. Like I said, this is in my PhD thesis, but kind of the motivating question for what I'm going to talk about today is essentially how to generalize this theorem. So somehow here this theorem is just for one orientation of the A and Dynkin diagram, but it's very natural to ask, well, if I pick another orientation of the A and Dynkin diagram and I look at the maximal green sequences of that modulo equivalence, is there some polytope that exists whose triangulations are in bijection with those maximal green sequences? So yeah, here's the kind of motivating question. Yeah, is there a similar bijection for other orientations of AN? And then a sort of kind of even more general version of this is yeah, how about for endomorphism algebras in the cluster category of arbitrary cluster tilting objects. So in particular, all reorientations of the AN diagram arise from cluster tilting objects, but one can choose cluster tilting objects whose endomorphism algebras are not just the path algebra of some reorientation. So essentially the answer to this question is yes, or at least I can prove that half of the bijection so far. But instead of looking at triangulations of polytopes, it actually makes more sense to look at triangulations of something more abstract than a polytope, namely oriented matroids, as I mentioned in the title. So, well, okay, so yeah, this theorem is work in progress, but this is something I can currently prove. So every cluster tilting object T in the cluster category of an AN quiver defines an oriented matroid MT such that firstly, so one. Every maximal green sequence of the endomorphism algebra of the cluster tilting object gives a triangulation of this oriented matroid. And secondly, equivalent maximal green sequences give the same triangulation. So this is currently, I suppose, one half of a bijection relating triangulations of this oriented matroid with maximal green sequences of the endomorphism algebra of T. And yeah, currently conjecture slash trying to prove this at the moment, every triangulation of this oriented matroid MT defines a maximal green sequence of the endomorphism algebra. Yeah, and we have a bijection. But yeah, somehow currently just trying to rule out pathological triangulations of this matroid. Okay, so let's go on and look at some more detail. So yeah, let me tell you a bit more about cluster categories and look at an example to make it a bit less abstract. So as I said before, they're defined by Buan, Marsh, Reineke, Reiten, and Todorov. So yeah, Q a quiver, K a field, and what we do is we take the bounded derived category of the path algebra of Q and yeah, take the orbits of the functor composed with the negative second shift. So okay, we're interested in these cluster tilting objects which live in this cluster category. So what are those? Well, an object T in this category is cluster tilting if firstly x1 of the object with itself in the cluster category is 0, and secondly if T has as many isomorphism classes of indecomposable summands as there are vertices in the quiver, so size of Q0. So yeah, Q0 is the set of vertices of the quiver. Okay, so we're particularly interested in this category when Q is just a quiver of type A, so an orientation of the A Dynkin diagram. And these were well studied kind of before the work of Buan, Marsh, Reineke, Reiten, and Todorov by Calderon, Chaforton, and Schiffler. And one can kind of describe them in terms of yeah, combinatorics of polygons. So I'm going to, because these are really the only case we're interested in this talk, I'm going to abbreviate CN to mean the cluster category of AN. And yeah, the orientation one chooses on the diagram always gives the same category. So yeah, I'm going to label the vertices of a convex n+3 gon anti-clockwise by the numbers from 1 to n+3, as you might expect. And okay, so we have a bijection between diagonals AB in our n+3 gon and indecomposable objects MAB in the cluster category up to isomorphism, of course. One can interpret the shift functor in the cluster category in terms of this model. So the interpretation of this is somehow just clockwise rotation of the arc. or of the diagonal. So yeah, we take the diagonal AB to A minus 1, B minus 1. And then one can also detect X1 very nicely in this model. So X1 between two indecomposable objects is non-zero if and only if the diagonals AC and BD cross. And of course, if you put these last two things together, you can also detect just homomorphisms in the ordinary way. But yeah, recalling that cluster tilting objects were defined to be things which have no X1 with themselves, and as many isomorphism classes of indecomposable summands as there are vertices of the quiver, it follows from what we said so far that there's a bijection between, on the one hand, triangulations of Vn plus 3 gone, and on the other hand, basic cluster tilting objects in the cluster category. Okay. So yeah, let's look at an example. Just yeah, sort of the smallest, slightly interesting example. So our quiver is just going to be this A2 quiver. So what are the indecomposable representations of this quiver? Well, there are three of them. So you can either have this, this, or this, and I'm going to denote this by 1, this by 1, 2, and this by 2. And yeah, the morphisms between these representations are like so. So this is somehow a picture of the module category of the path algebra of A2. In a similar way, we can look at the derived category. I guess by work of Happel, because this is a hereditary algebra, we know that all of the objects in the derived category are just stalk complexes. So one can draw the derived category like so. Then we want to look at the cluster category. So a category of orbits of the Serre functor composed with the negative second shift of this. Okay, so how does the Serre functor act on the derived category? Well, it essentially just kind of moves objects forward like so. And so without kind of verifying all of the detail, one can check that the fundamental domain of the Serre functor composed with the second shift is just this part of the derived category, and that this then starts repeating when one takes the cluster category. So one gets something that looks like this. So how does this work? So okay, after 1, 2 shifted by 1 in the cluster category, we get 2. So why is that? Well, if we take the object that's there in the derived category 1, 1, and then we send it we apply the surf functor to it, then we go to the object here, which is 2 shifted by 2. And so then when we shift that back by -2, we get 2. So we can pick 2 just as the representative of this orbit of the functor nu composed with negative second shift. Okay, yeah, so we get this triangulated category which only has 5 indecomposable objects. How does this map up in terms of the diagonals of the polygon? Well, it's like so. So 2 corresponds to the diagonal 1, 3. 1, 2 corresponds to the diagonal 1, 4. 1 corresponds to the diagonal 2, 4. And yeah, 2, 1 is 2, 5. And then 1, 2 shifted by 1 is 3, 5. And then yeah, it keeps going. And you can verify essentially the statements I made above about how the shift functor acts. So yeah, if we shift M13, we go to M25. So yeah, 1 minus 1 is 5 in this context, and 3 minus 1 is 2. So that's how that works. Okay. So that's a bit of our cluster category. So yeah, now let me move on and start talking about maximal green sequences, which I guess are the important players for us. So for the purposes of this talk, I'm going to give a slightly non-standard presentation of these, which is the reasons will become obvious when I define these oriented matroids, but we're going to introduce them by essentially changing the X triangulated structure on the cluster category. So I'm not going to fully define X triangulated categories, but they kind of generalize triangulated categories. They're introduced by Nakaoka and Palu. In some ways, they are the triangulated analog of exact categories. So they are a little bit like what exact categories are to abelian categories. But actually they also include exact categories. But okay, what do they mean for us? So for us, the point is we will take a new X triangulated structure on Cn by taking a subset of the distinguished triangles of Cn. So yeah, for us, they are kind of a bit like exact categories in the sense that one way you can think about exact categories is if you have an abelian category, you can change the exact structure by just taking a subset of the short exact sequences. For us, we're kind of treating them similarly. We have a triangulated category, and we're going to change the X triangulated structure by taking a subset of the distinguished triangles. So what subset are we going to take? Okay, so given a cluster tilting object T in Cn, define the X triangulated structure consisting of the triangles x to y to z to x1, where this morphism H factors through the shift of our cluster tilting object T. So this is an example of a relative X triangulated structure introduced by Hershey and Liu and Nakaoka. And this particular X triangulated structure was considered by Padrol, Palu, Pilot, and Plamondon. And we're going to denote by math bold E subscript T, ZX, the set of equivalence classes in the obvious sense of such triangles for X and Z. Okay. So what this then allows us to do is okay, so maybe if we backtrack a bit, so you'll notice this X1 condition on the triangulated category is symmetric. So AC and BD cross, that's a symmetric condition. So we have the X1 MAC and BD is non-zero if and only if X1 MBD MAC is non-zero. So yeah, these two things are always equal. And essentially by taking only a subset of the triangles, we're essentially going to be throwing away one of these two. So we're kind of insisting that these extensions actually have a direction. And this allows us to have this notion of green mutation, which allows us to define maximal green sequences. So maximal green sequences are due to Keller under a sort of combinatorial definition using quivers. There are lots of different characterizations of them in the literature, and yeah, one can also define them as follows, but I don't think anyone else has kind of written this in the literature before. But okay, I'm going to let L and L prime be two basic cluster tilting objects. In our cluster category with X and Y indecomposable. Such that the extensions the extensions in this relative X triangulated structure from Y to X are non-zero. Yeah, and in this case, we say that L prime is a T green mutation of L. Yeah, green with respect to our sort of chosen cluster tilting object T. Okay, and now we have this notion of green mutation, we can say what a maximal green sequence is. So yeah, given a cluster tilting object T, so yeah, a maximal green sequence somehow to me it makes most sense to call this a maximal green sequence of T, but this is somehow equivalent to what one would usually call a maximal green sequence of end of T. Is a sequence. So we start with a cluster tilting object. We start with T0, which is just equal to T. And we end with TL, which is equal to T shifted by 1. And for each I, Ti is a T green mutation of Ti minus 1. And okay, I told you there was some notion of equivalence of maximal green sequences, which I defined with Michal Gorski. So here it is, yeah, two maximal green sequences are equivalent if yeah, they have the same sets of indecomposable summands. So you look at all of the cluster tilting objects that occur in the maximal green sequence, you look at the indecomposable summands of each of them, and you take the set of all of those indecomposable objects, and this is what determines the equivalence class. Okay. So now I've introduced all the notions, let me quickly restate my theorem from earlier, the theorem that is out, which is, yeah, there's a bijection between maximal green sequences of the path algebra of yeah, linearly oriented AN. So we pick a cluster tilting object whose endomorphism algebra is linearly oriented AN modulo equivalence, and yeah, triangulations of 3-dim cyclic polytope with n+3 vertices. Okay. So yeah, so now let me get on, I guess, to the new stuff, which is, yeah, work in progress. So yeah, extending this to other cluster tilting objects. So yeah, here's a restatement of our earlier question. So yeah, given a cluster tilting object T in the cluster category, is there a polytope PT whose triangulations are in bijection with maximal green sequences of T. So somehow the problem with this question, which I kind of mentioned earlier, is that well, I hinted at earlier, I guess polytopes are hard to realize somehow. I mean, you might have some combinatorial structure which you think kind of defines a polytope, but it's hard to actually you know, specify actual you know, points in space which give you that combinatorial structure. And yeah, also somehow, yeah, similarly, polytope is more information than we need, because you don't per se need to find a kind of realized polytope. Yeah, instead we can just look at this abstract structure, which gives us the information we're interested in. So yeah, the combinatorial info we are interested in is coded in yeah, a certain structure called an oriented matroid. So yeah, I'm not going to define this, but let me give you an idea of what it is. So let E be a set of n vectors in R to the R, set of n I guess distinct non-zero vectors which span real R-dimensional space. Then so in some ways, if you have a polytope, you can get such a configuration of vectors from it. So yeah, the kind of oriented matroid or pyrotope, which is what you call this kind of particular way of, I guess, thinking about oriented matroid, is the map chi, which goes from e to the r to 1, 0, -1, which sends a tuple of these vectors to the sign of the determinant of the matrix with these columns. R here is the rank. So somehow if we were just to forget the sign of the determinant, but just remember which sets of R vectors actually gave us a basis of R-dimensional real space, this would just be a matroid. So yeah, somehow remembering the sign is what makes it oriented. Okay, so this is somehow the oriented matroid you get from a configuration of non-zero vectors. In general, for E, an abstract finite set, can define a rank R oriented matroid on E to be a map, similar looking map from E to the R to -1, 0, 1, satisfying some axioms. Which it's probably best not to give the details of. One can define triangulations, sort of a subdivision into simplices of oriented matroids. In a way that generalizes triangulations of polytopes. Okay, so as I told you at the beginning, what we're going to do is define an oriented matroid, whose conjecturally whose triangulations correspond to maximal green sequences of our chosen cluster tilting object. And this will somehow explain why I've introduced maximal green sequences in the way I did using this certain relative X triangulated structure, because the oriented matroid itself is going to be defined also by this relative X triangulated structure. So let's look at the definition. Let T be a cluster tilting object in Cn, and we're going to define the following rank 4 chirotope on this set from 1 to n+3. So, okay, I'm going to let A, B, C, and D be elements of this set ordered like so. Then okay, so our rank 4 chirotope is going to be called chi-t. Chi-t of A, B, C, D is going to equal +1 if the sort of relative x from the x triangulated structure between M, BD and MAC is non-zero, and -1 if in fact the other direction holds. And yeah, of course this is well defined, only one of these can hold, it turns out. And yeah, the first theorem is because, like I said, this has to obey some axioms in order to give us a well-defined oriented matroid, is that yeah, this is in fact a well-defined oriented matroid. Yeah, which is somehow, I guess, like a nice perspective on what the choice of relative X triangulated structure gives us in terms of the geometric side with the polygon. It's somehow, yeah, like a choice of orientation somehow. And okay, I quite near the end of the talk actually, so yeah, it's just taking a bit less long than I thought, but that's okay. So okay, so what's our next theorem? Every maximal green sequence of our cluster tilting object T gives a triangulation of chi T, and equivalent maximal green sequences give the same triangulation. And then, yeah, the part which is still conjectural is as follows, that, yeah, every triangulation of this oriented matroid chi T gives an equivalence class of maximal green sequences, and that, yeah, this gives the inverse construction to above. Okay, so I thought of something I can do with the extra time. So yeah, I was thinking actually I could do this, but perhaps I can well, give an A2 example of the sort of earlier theorem showing how cyclic polytope triangulations correspond to maximal green sequences of A2. So, okay, so we had our A2 cluster category looking like this. Oh yeah, it continues on both sides. And this corresponds to diagonals like so. Yeah, again, it continues. So let's start. So okay, so 2 plus 1, 2 defines a cluster tilting object. You know, in terms of triangulations, it's the diagonal 1, 3 and the diagonal 1, 4. So yeah, we get this triangulation, which shows that this is actually a cluster tilting object. This admits 2 T-green mutations. So either we can mutate 2 and get 1 plus 1, 2. So that's flipping at 1, 3. Like so. Or we can send 1, 2 to 1, 2 shifted by 1. And so that corresponds to this triangulation. Okay, on this side, there's 1 T-green mutation, which I guess swaps 1, 2 for 2 shifted by 1. So, and oh wait, I made a mistake. I flipped that one too early. But yeah, that why I should start just copying these things because yeah. Yeah, and that's the one we flipped now. And then yeah, the final cluster tilting object is 2, 1 plus 1, 2 shifted by 1. So yeah, just the original cluster tilting object, but shifted by 1. And we get this triangulation. Okay, and then in terms of okay, so we have two maximal green sequences, namely the one that goes through this sequence of mutations and then the one that goes through this sequence of mutations. So we can expect that each of these should give a different three-dimensional triangulation. I guess one can also verify that these two maximal green sequences are not equivalent because the left-hand one contains 1 as an indecomposable summand, whereas the right-hand one does not. So the way to get a three-dimensional triangulation from this is we look at the quadrilaterals where the flips occur, and the flip can kind of be conceived of going from one side of a three-dimensional simplex to the other. So this flip gives us this three-dimensional simplex. So it's 1, 2, 3, 4. And then similarly, the flip here gives us this three-dimensional simplex. And yeah, finally, we get this three-dimensional simplex. So yeah, 1, 2, 4, 5. 2, 3, 4, 5. So that's a collection of three-dimensional simplices on the left-hand maximal green sequence. Then over here, the first mutation corresponds to the following. 1, 3, 4, 5. And then the second mutation corresponds to this three-dimensional simplex. 1, 2, 3, 5. Okay, and now what we do is we if you put the three simplices together, then what we get is a triangulation of this three-dimensional polytope. So yeah, hopefully sufficiently good drawing. So yeah, we have a three-dimensional polytope which looks like this, and this is indeed a three-dimensional cyclic polytope with 5 vertices. And on one side, we have a triangulation that looks like this. Triangulation of this into three-dimensional simplices. One, two, three, four, 5. And on the other side, we get this triangulation into two three-dimensional simplices. Okay, yeah. Triangulation number 1 and triangulation number 2. Okay. So yeah, maybe this is a good place to finish.
Thank you. Thank you, Nick. Let's all give the speaker a round of applause now. So if you have any questions, please ask them now.
Hello. So I just want to ask one quick question.
Yeah, sure.
So I just want to check if I understand your results correctly.
Yeah,
So
yeah, sure.
in terms of, let's say, this writing this cluster tilting, I mean, like this extended version. So your result only contains the d=1 case, or is it okay if you apply tilting, let's say more than 2? You know, let's say in this case, it's maybe like 2 bracket 2 or something like that.
I'm not sure. I'm not sure I totally understand the question. So when you say d=1, like what's
Oh,
d
so what I
there?
mean by d is I mean like the number inside this bracket that you just explained in this example.
Oh, so the number in the square brackets.
Mm-hmm.
Oh, okay. Right. Yes. Okay. Yeah. So yes. Thanks. So yeah. So you're right that so I guess what you're referring to is perhaps where is it? So this result I wrote here. So there is actually a kind of a higher dimensional version of this result, which is also in my thesis, which is, yeah, if we chooses D maximal green sequences um, of, yeah, a Dn, then, yeah, one gets triangulations of a 2D plus 1 dimensional cyclic polytope. So, yeah, you're right. What I've been talking about in this talk is just for D=1. So yeah, I believe that one should be able to also for other cluster tilting objects yeah, in sort of the higher dimensional cluster categories, define oriented matroids whose yeah triangulations are in bijection with the D maximal green sequences. Yeah, somehow when D is greater than one, it just becomes much harder. So yeah, I mean I think in principle everything should still work, but
Yeah, I mean, the reason I thought
yeah.
that way is that, like, I mean, you know, the paper by Opperman and Thomas actually, they
Yes,
actually talk
yeah.
about the general decay. So that's why I thought that, let's say,
Yeah,
maybe
yeah,
your
yeah, yeah,
result can be.
exactly. So yeah, no, thank you. It's a good question. Yeah, I don't have any results for D greater than one at the moment.
I see.
It is definitely harder, but yeah, I think things should still work. But yeah, I didn't
Okay,
really
I mean, I just wanted
to
to
try
check
and
if I understand your
yeah,
result
yeah, yeah.
correctly.
No, but yeah,
Thank
yeah.
you.
No, you're understanding 100% correct. Yeah.
I see. Okay, cool.
Yeah.
Thank you.
Thank you, Wanda. Any other questions?
Hi, Nick. I just have a quick
Hi,
question,
Monica.
like more
Yeah.
a combinatorial one.
Yes.
So choosing your tilting object is like fixing an initial triangulation. Can we easily
Yes.
see, just looking at the triangulation, whether a flip is green?
Yeah. That's a good question, and yeah, yes, you very much can, and it's somehow to do with the criterion is more or less as follows. So if you take so I'm looking at like the 1, 2, 4, 5 simplex here. So it's somehow you look at your like initial triangulation, and it's something like there must be a diagonal in the original triangulation which like kind of intersects like the simplex kind of either that way or that way. And essentially it's going to be green if it's like that way, with sort of that being a limiting case. So yeah, you can very much see it in terms of the initial triangulation, and yeah, that's somehow actually like how the proofs work, is to translate this criterion you get just in terms of the X triangulated structure, which is somehow
Mhm.
like the motivation for defining this thing, but then yeah, translate what it means back into the triangulation, and then that's yeah how you prove things. But yeah, thanks for the question.
Thank you for the answer.
Thank you, Monica. Any more questions? I'm guessing the conjecture that you ended your talk with, well,
Yes.
is born out of like what sheer numerical, not numerical evidence, but just sheer evidence. Is there an intuition
Well,
behind?
yeah, I mean, to be honest with this, like it essentially what you have to prove is just that there don't exist like really pathological triangulations of these matroids. So somehow like when you have a triangulation of this matroid, there's like a natural way you want to partially order the simplices in order to sort of give you the sequence of mutations, and like the only thing that can go wrong is if that partial order is not actually a partial order and contains a cycle. And so that's what you want to try and rule out. And yeah, in all examples I've looked at, there are no cycles, and it's sort of like, seems very reasonable that like, things won't ever go around in a cycle, but it's just trying to prove that rigorously. That's the tricky thing.
Do you guys get this as a conjecture in the paper?
Well, I mean, so this isn't out yet. So yeah, my hope is that yeah, once the paper is out, this will have transformed from being a conjecture into a theorem.
Okay, cool. Okay.
But yeah, currently I can't prove it, so I wouldn't want to state it as a theorem. But yeah, hopefully future theorem.
Yeah, I mean, no, sometimes people are happy with calling something a conjecture in talk, but then they don't call it a conjecture in written form.
Yeah. So I'm not quite at that stage yet. Yeah, this is still something I can't prove, but yeah, I believe it's true, and yeah, hopefully can prove.
Okay. Thank you.
Thanks.
Any more questions, anybody? If not, let's thank Nick once again. We have, thank you all for coming. We have Mikhail Bondarko speaking next week. Hope to see you there. All right.